Okay, so today we will start with a new chapter, partial differential equations. Partial differential equation is a very big subject. So in this chapter, we just try to solve simpler partial differential equations. Okay. Right. So the first section is about a basic concept of partial differential equations. The first concept is about classification. So there are a lot of partial differential equations. I will classify. The first is called linear PDEs. Okay. So the linear PDEs they are PDEs which are which are of the first degree, right, in the unknown function u and its partial derivatives. For example, a general second order linear PDE, in two variables x and y. Is of the form. Right. So second order means that because every partial derivative of a function has an order. For example, the unknown function u itself is of the order 0. And the first partial differential partial derivative of a function would be called first order 1. So I think you all know the order of partial derivative of a function in calculus, right? Do you know that? Never mind. Well, if you have any question, just raise your hand. So so an example would be a1 xy and u xx. So what is u xx? It is the second order partial derivative of u respect to y, with respect to x. All right, and plus a2 and u xy plus a3 and uyx plus a4 uyy plus a5. So these four are partial derivatives of second order. And this is the partial derivative of first order, right? So we have, because we have two independent variables, x and y, so that we have only two first order partial derivative. But we have four right? We have 4 partial derivatives here for second order. Okay. And how about third order? How many partial derivatives do we have for three order? 8, right? 2 to the 3rd power, 8. How many for fourth order? 2 to the 4th power, 16, etc. So if you have the number of nth order partial derivative is 2 to the nth power. Okay, so that is the general case. Okay, and then finally, 0 order, only 1 0 order, right? Partial derivative, that is the U itself. So it's A7 and U, and plus, okay, plus constant. So we say fxy. Maybe I should write it more compact. Plus A7 xy u, okay, plus f of xy is equal to 0. So this is the most general form of second order, because so the order of a partial differential is the order of a partial derivative to appear in the equation. So you can see these 4 are all possible second order partial derivative of u. Okay, and you can see the coefficients. The coefficients are functions. So where ai and are functions of independent variables x and y only. Okay, so that the coefficients do not depend on lower order partial derivatives, just independent variables only. Okay, so sorry. Okay. All right. So this kind of this is the general second order linear PDE. Okay. All right. From this example, you can extend it to general nth order linear PDE. Okay. And so the terms. So the number of terms will be. You can see it's so the number of terms here is 8, right? Excluding the inhomogeneous term here. All right, excluding that. So how many terms do we have? Well, here in general we have so for general nth order linear PDE, we have I from 0 to n to the i's power, okay, plus 1. So will be, yeah. And what is that? It is equal to n plus 1's power. Okay. So we have such many terms. Okay. So for an nth order linear PDE, we have, in general, we have 2 to the n plus 1's power terms. Any questions? And the coefficients. All right, so you can see each partial derivative appear in of 1 degree, right? in the first degree. So u x y is in the first degree, everything is in first degrees. But the coefficients are functions of independent variables. Okay? All right. And also, if the coefficients AI, x, if the coefficient AI is constant, are constants, okay, means that independent of x, x and y, then the PDEs, are called linear with constant coefficient. Okay, so if the coefficient, not including the f function, okay, f function can be still arbitrary, but the coefficient AIs, all right, if AIs are really constants, then such a PDE is called linear PDE with constant coefficients. Okay, and if f of x equal to 0, so if then the PDEs are called homogeneous linear PDEs. Okay. All right. So the most simplest PDE would be homogeneous linear PDE with constant coefficients, right? So f disappear and all the coefficients are constants. Okay. All right. So and examples. So important examples of second order linear PDEs with constant coefficient. Right. So which will be studied, in this chapter. So one-dimensional wave equation. One-dimensional wave equation described okay. So this is the second order partial derivative with respect to time, t. Okay, and c square. And this is the second order partial derivative of u with respect to the space coordinate x. So And we have only one spatial dimension x, so it's called one-dimensional wave equation. So that is to describe the wave traveling along the x-axis, just one-dimensional, as time goes on. Okay, so so we have two independent variables. One is the time t, the other is the spatial dimension x. So it's called one-dimensional wave equations. All right. And when we study the EM waves, then the simplest EM wave would be the one-dimensional EM wave. All right. So that would be propagate through one direction. Okay. So the first one. The second one would be one-dimensional heat equation. Okay, so that would be right. Will be this is the first order partial derivative of the u. Okay, and so representing the convention of heat. All right, and so this is about the time equal to the second order partial derivative of u with respect to the spatial dimension x. Okay, so it's one dimensional because we assume the heat will propagate in one direction. Okay. Third one, two-dimensional Laplace equation. So two-dimensional Laplace equation, it's something about the steady state phenomena. So we assume that the time has been going to the steady state, so that all the system has been in the equivalent state. So the system, the stable system, will not evolve along the time. Okay, so the quantity, the physical quantity u, depends only on the spatial dimension x and y. Okay, so this one is about the second order partial derivative with respect to x plus second order with respect to y equal to 0. Okay, so this is called the second two-dimensional Laplace equation. All right, and the third one. So you can see these three are all homogeneous. Okay, so these three linear PDE with constant coefficients, they are all homogeneous. Now the fourth one is called two-dimensional Poisson equation. All right, basically very similar to the Laplace equation, but it is inhomogeneous because it has fxy. Okay, so that it is inhomogeneous. Okay, so it's inhomogeneous. The fifth one. Two-dimensional wave equation. Okay, so the two-dimensional wave equation is very similar to the one-dimensional equation, except that in addition to so they are two spatial variables, right? So it describes a plane wave, okay? It's a plane wave, and so we have okay. So they all involve second order partial derivatives. Okay, they are called and three-dimensional Laplace equation. All right. So now we consider steady state equilibrium that in the space. Okay, and so the last two also again is homogeneous. Okay, so in these six examples, 5 of them are homogeneous. Only 1 of them inhomogeneous. Okay, so they are. Okay, so this is the first type called linear PDE. So linear PDE will be our main topics in this chapter. All right. Okay, and the second is called nonlinear PDEs. Okay, but nonlinear PDE is very broad. Okay, and so will be classified into 3 different subtypes. All right, so that they are three main types of. There are 3 main types. Okay. One is called the semi-linear PDEs. The second one is quasi-linear PDEs. And the last one is called the fully linear, nonlinear PDEs. Okay? And the fully nonlinear PDEs here. All right. And so we will take some examples to show how do we say. All right, so 2A, semi-linear PDEs. Okay, semi-linear PDEs, all right, are nonlinear PDEs which are near raised to linear PDEs. And where only the highest order derivatives appears, right, as linear terms. Okay, with coefficient that are functions So that are functions of the independent variables only. All right, so let's take example. For example, in here we have a general second order linear PDE, right? So a general second order semi-linear PDE in two variables, right? Is of the form. Okay. So now we say that it is very close to linear in that the high order term, the highest order term. So in second order, the highest order term would be this 4. And this 4 order term appears, right, linearly. Okay? Appears linearly. With coefficient depends only on independent variable x and y. So it will keep, so that they will keep the same but for all low order terms, including ux, uy, u, and xy, they can be arbitrary. For example, you may have the square of ux, you may have the third power of uy, you may have fifth power of u in itself. So that this becomes to be a function of, all right, so everything can be included in this function, and f can be arbitrary. Okay? Can be arbitrary here. So only the highest order term, right, would be the same as the linear, okay, as the linear PDEs. And the rest can be arbitrary. So this may involve some nonlinear terms of ux. For example, ux times uy, for example, would be one of the terms in the function. So f can be arbitrary. So this PDE is a second order semi-linear PDEs. Okay, so it's 2A. Right. How about 2B? Quasi-linear PDEs. So what are quasi-linear PDEs? For quasi-linear PDEs, have the highest order derivative. Okay. To appear to likewise appear only as linear terms. All right? Okay. But with coefficient. So the difference, what is the difference? With coefficients, possibly function of the unknown and low order derivatives. So for example, all right, a general second order quasi linear PDEs in two variables. Okay, is of the form. So what different? In semi-linear PDEs, the coefficient of these four high-order terms are functions of independent variables. But in quasi-linear, all right, the coefficient will be arbitrary function of the unknown function and its low-order derivatives. In here, the low order means the first order or zero order, right? Two first order partial derivative and the zero order, and the x and y, and the uxx plus a2, ux, uy, uxy, uxy plus a3, ux, uy, uxy, uyx plus a4, ux, uy, uxy, uyy plus f, ux, uy, uxy equal to 0. Okay. So the highest order derivatives appear in linear. Okay, appear because they are only of the first degree, right? But the coefficient may include not just two independent values, but also the unknown function u as well as the low order derivatives here. Okay, so this is the situation. And the 2C, fully okay. So fully nonlinear PDEs, okay, possess nonlinearity on one or more of the highest order derivatives. All right, let's take an example. An example, okay, is the Monge ampere. So it's the Monge ampere equation. Okay, so the equation is here. Is the A0 ux uy uxy, and we have the product of uxx uyy minus uxy uyx. Okay, so you can see this is of second degree, right? You have nonlinearity of the highest degree, and the highest degree in here is the second degree. Okay, so this is a second degree fully nonlinear PDE. Okay, so you have these terms, and you may have the other terms. So you have ux, uy, uxy plus a1, uxy plus a2, a2, sorry, and a3 of ux, uy, uxy, uyx plus a4 ux, uy, uy, and uyy plus f of ux, uy, uxy equal to 0. Okay, so this is so-called fully nonlinear. Okay, because we have nonlinearity on 1 or more of the highest order derivatives, especially here. Okay, you can see that. You see. All right, so this equation is called the Monge-Ampere equation. All right, so this is, you can see we describe and all possible partial differential equation PDEs. Okay, and we will focus on, of course, we will focus on the most simplest ones in this chapter. All right, to get the first introduction to PDEs. Okay, that is the purpose of this course. Otherwise, given you 1 year, you can't cover all the subject of the PDEs. Okay. Any questions about clarification? All right. Now, so now we will, so a domain in an Euclidean space, right, is an open connected subset of Rn. Okay, right? So we will use the region, a domain. So domain, because we are talking about maybe it's one-dimensional or two-dimensional space or even three-dimensional space. And so we will specify the subset in the Euclidean space for all the points that the differential equation is satisfied. Okay, because it's quite often that you can only say that a differential equation is satisfied within some subset of the Euclidean space. Most often you can't say that it satisfies for all the points in the whole Euclidean space. Okay, that is not practical. Okay, so quite often, and we will introduce a special subset called domain, which is open and connected. Okay, connected set. And also, we will have a geometrical concept called region. So a region in Rn, okay, is a domain. All right, so it's a domain plus, right, plus none or some or all of its boundary points. Of course, if a region does not include any boundary point, then such a region is just equal to a domain. Okay, it's just a domain. But sometimes, so let's see in R2. Let me take some examples. All right. So in R2, So the shaded area, okay, the shaded area here, without including the boundary, so this is a domain. Okay, a domain here. And if you include some boundary point, it is open, of course. It is connected. Why it's connected? Because you can connect 2 points in the domain by path, by polygon. So, for example, if you have point P here, and you have a point Q here, they can be connected. How? Well, you can use polygon. 1, 2, 3, 4, 5. So you can always reach to, so any 2 points can be connected by polygon. Okay? So that they are connected. So it's a domain. It's domain. And if you include some point, okay? So a domain D, okay? And this is some boundary, okay? So that D union it's a region, okay? It's a region. And if you have 2 disjoint open disk, okay, together, so together, so not a domain. Even though the union, okay, union these 2, so okay, so they did not touch each other. So these 2, so maybe you have D1 here, D2 here, D1 intersect D2 is the empty state. Then D1 union D2 is not a domain, because it is not connected. Because if you pick this is P, this is Q, you can't connect Q and P by polygon. You can't, because they are disjoint from each other. Okay, so this is not a domain. The union of D1 and D2 are not domain, even though D1 itself is a domain, right? D2 a domain again, but the union of these 2 domains together is not a domain anymore. Okay, so any questions about the concepts of domain and region? All right, now, so a solution, we want to solve PDE, right? So a solution of a PDE in some region, say R, of the space of the independent variables. Okay, it's a function. Okay, it's a function U. Okay, that has the partial derivative appearing in the PDE. Okay, so that, for example, if in here is a second order PDE, then then they should have second order PDE, partial derivative, okay, involving in the PDEs. Okay. All right, in some domain. Okay, in some domain D containing R. Okay, so we say a solution in some region. So region R is the subset of the space of independent variable we are interested in. Okay, and so the D, so that so the situation is here. So this is D. So D is an open connect set, right? And so this is D. And the region we specified is here. This is R, our region here. Okay, so that a solution of PDE in this region, okay, then we mean a function. This function is partial derivative appearing in the PDE in the domain D. So maybe in a bigger open set. Okay, so that all the partial derivatives will exist, all right, over the bigger domain. Okay. All right, and satisfy. Okay, the PDE everywhere in R in the region. Okay, all right. So at every boundary point, the partial derivative of U also exists because every boundary point also in the D. So that we can talk about the partial derivatives. Because to find partial derivatives, we have to look at a neighborhood of a point. Okay, so a neighborhood of a point here, of a point on the boundary would be including points in the region and outside the region. Okay, to find the partial derivative at the point. So we have to know that. That's why we require a domain D bigger than the region R. Okay, so it's essential to know that, right? And so that the equation, the partial derivative equation, is satisfied everywhere in the region R. So that is called a solution. Okay. All right. And in general, okay, the totality of solutions of a PDE is very large. Okay, let's take an example. For example, the following function u equal to x squared minus y squared, u equal to e to the x power, and cosine y, u equal to sine x, hyper cosine y, and u equal to the logarithm of the sum of x squared and y squared. You can see these four kind of functions are very different from each other, right? So they are quite different, right? But they are solutions, okay, of the two-dimensional Laplace equation. Here, the two-dimensional Laplace equation, this equation. Okay, so these four different kind of functions are solutions. All right, so you can see the solution of PDE is more complicated than ordinary differential equations. All right, so that is the way we have to do. Okay, all right, and the unique solution, okay, of a PDE corresponding to a given physical problem okay, will be obtained by the use of additional condition arising from the problem. So, for example, if you are solving the Laplace equations, then as it being shown here, they are quite different solutions, different type of solutions. So unique solution, okay, because for any physical problems, you should have a unique solution. Why? Because of causality of the physical problems, especially in classical mechanics. So, so the unique solution can be obtained by use of additional condition. For example, the initial condition and as the boundary condition, such as boundary conditions okay, on the boundary of the region R. Okay, our initial conditions at time equal to 0. Okay. Okay, so we will learn how to solve if we know that they are unique solutions. So we try our best to find a solution. Why? Because if we find a solution, that should be the very solution you want. But if you are talking about general solutions, for example, if you want to find the general solution of Laplace equation, that would be a big subject. Why? For example, you see these four kind of functions are possible solutions of the Laplace equations. So how can you describe the general solution? That is a big problem. Okay, so that physical approach is that you try to find one, because you know from the physical problem, you know that this has one solution, unique solution. All right, and so you try to find one by many different kind of techniques. That is one of the approach. Otherwise, if you want to find general solution, then you should lay your foundation more. Okay, okay. So I stop here, and on Thursday we will have first midterm examination. The starting time will be 12:40. All right. earlier, much earlier than the usual class time, right? Because I want you to have more time to do the exam problems. Okay, so that would be from 12:40. Remember that, okay? And we don't have quiz exam next week. Good. I will announce this later in the E class platform. All right, so let's stop here.